So could we use enthalpy for a chemical potential? So if you remember from Chem 1A, the change in enthalpy for a chemical process is equal to the heat exchanged with the surroundings at constant pressure. So we've kind of, I think, become familiar with, well, if delta H is negative, then it's releasing energy. If delta H is positive, it's absorbing energy. The surroundings are going to get cold. So could we use this as our guide for is it spontaneous or not? And no, we can't, because enthalpy would predict that all exothermic reactions are spontaneous and all endothermic reactions are not spontaneous. But that's not the case. There are some endothermic reactions that are spontaneous. Can you think of any? Ice melting. Yeah. How about those instant ice packs, those instant cold packs, where you break the little seal and the chemicals mix and it gets cold all by itself? That's an endothermic reaction, but it's spontaneous. So there's got to be more to the story than that. So the melting of ice above 0 degrees Celsius, that involves an increase in enthalpy. Liquid water evaporating, it's an endothermic process. Sodium chloride dissolving in water, also an endothermic process. What do these things have in common? They've got water in common. Excellent. Not the answer I was going for, but absolutely true. In each of these processes, disorder or randomness is increasing. And entropy, which was also introduced in Chem 1A, is actually the criteria for, criterion singular, for spontaneity in chemical processes, chemical systems. So informally, we can think of entropy as disorder or randomness. If we look at a couple of these processes, here we have sodium chloride dissolving in water. In sodium chloride crystals, the sodium and the chloride ions are arranged in a very rigid pattern. It's sodium chloride throughout. When this dissolves in water, those ions disperse throughout the water and they no longer have that order that they had before. So a solution of sodium chloride is more disordered than sodium chloride crystals. Does that make sense? Here we have water evaporating, and liquid water, the molecules are all very close together. They're confined to a smaller volume, and when they evaporate and go into the gas state, they spread out, and so that is an increase in disorder. So we use the symbol S for entropy. Have no idea why. It's a thermodynamic function that increases with the number of energetically equivalent ways to arrange the components of a system to achieve a particular state. So how many ways can the particles of the system be arranged and yet still have the same energy? That's what entropy is. So we can write an equation for entropy. Entropy is equal to a constant K times the natural log of W, capital W. So K is the Boltzmann constant, which happens to equal the ideal gas constant divided by N. And W is the number of energetically equivalent ways to arrange the components of the system. So the units of entropy end up being joules per Kelvin. So that doesn't seem very useful, does it? So imagine a fixed amount of gas. We've got constant volume, constant pressure, constant temperature. So we define the state of the system by monitoring the pressure, the volume, and the temperature. Under conditions of constant PV and T, the energy of the system is constant, right? But exactly where that energy is at any given instant is anything but constant, because the gas particles are moving around and they are changing their kinetic energy. The average kinetic energy is remaining the same, but when two gas particles collide, energy is conserved, but energy can be transferred from one to the other. So, upon collision, a low energy particle might become a high energy particle. That make sense? So if we look at it from our point of view, where we can't see the individual particles, it looks like this thing is constant. The energy is the same, because the pressure, the volume, the temperature are not changing. But if we could zoom in and look at the individual particles, we'd see that there's a lot going on. So the microstates are like a snapshot of what's going on in terms of energy distribution. So the exact internal energy distribution among particles at any one instant. That's a microstate. So the macrostate is the overall condition, pressure, volume, temperature of the gas. That is constant. That's the macrostate, the big picture. Given macrostate can have a large number of different microstates. I thought of an analogy. It just came to me, so hopefully it's going to work as I talk about it and play it out. So I don't know about you, but I get a kick out of looking at the Maps app on my phone. It's got this satellite picture, right? And you can zoom in and see that oil spot on the road in front of my house from my old Mustang. And, you can see, oh, yeah, this was taken before the neighbors put in their pool or before somebody chopped down that tree. It's just kind of cool, right? And sometimes in, more metropolitan area where the resolution's a little better, you can actually see people and their shadows, right? And it's like crazy. If you zoom in like that, that's like one microstate. Because are those people still there? No, that was probably taken months ago. And if you took a picture like that, even every second, it's changing, right? Cars slow down for a stoplight, they speed up, people are moving back and forth, all sorts of things are happening. But from the satellite view, big picture, zoomed out, it doesn't look like anything's happening. Does that make sense? So that one macrostate can have a lot of different microstates. So the microstate changes not its overall energy, but the distribution of the energy, okay? And so we can think of that capital W as the number of possible microstates within a given macrostate. So you can see that could be a really, really big number. So we're going to look at two systems that are very simple. They each have two particles, just two particles, and they have a total energy of 4 joules. So here's our two systems, System A and System B. In System A, there is only one energy level, and so both of those particles are at the same energy level of 2 joules, and there's only one possible state, right? In System B, there are 2 levels. There's a 1 joule level and there's a 3 joule level. So in order for the total energy here to be 4 joules, one of the particles is on the 3 joule level and one is on the 1 joule level, right? So we can have this microstate where the blue has 1 joule and the red has 3 joules. But there's another possible microstate where the blue one has 3 joules and the red one has 1 joule of energy. Overall, same macro state, right? But these are different. Yeah, but it's just a different particle, the same kind of particle. Yeah, but, if these are two people and these are their incomes and this guy's getting, $300,000 a year and this guy's getting $100,000 a year, and we'll just trade places, are they going to be cool with that? No. Those are different particles, and even if they're the same kind of atom, they are still different particles, right? And so having different energies is different microstates. So system B has 2 microstates, system A has 1 microstate. So the entropy is proportional to the number of microstates, so system B has greater entropy. Any questions? Because I don't think it's possible to make it any simpler than this, so of course it's going to get more complicated. So if it's not making sense right now, please ask. Okay. So the entropy of a state increases as you increase the number of energetically equivalent ways. Okay. The state with the highest entropy also has the greatest dispersal of energy. So in system B, the energy of the system was dispersed over 2 levels. In system A, it was only dispersed over 1 level. So if we have the energy being more highly dispersed or more highly randomized, that state has more entropy than a state in which the same energy, is more highly concentrated. Which brings us to the second law of thermodynamics. For any spontaneous process, the entropy of the universe increases. The universe is getting messier. So the criteria for spontaneity is the entropy of the universe. If the entropy of the universe is increasing, because of that process, it will be spontaneous. If the entropy of the universe is decreasing, it's not spontaneous. Entropy is another one of those state functions where the value depends on the state of the system and not on how it got there. Like a change in elevation, the difference between where you start and where you end up is the same regardless of how you got there. So the change in entropy is the final minus the initial. So chemical systems proceed in a direction that increases the entropy of the universe. So let's look at this. Here we have 2 sealed containers connected by a stopcock in the middle so that we can allow things to pass or stop things from passing. Initially, what we have is 4 gas particles over here and nothing over there. There's just not even air. This is a perfect vacuum. So there's literally nothing there. So if we open the stopcock, what's going to happen? These gas particles are going to start moving over there, right? Because these gas particles do what gas particles do, and they bounce around till they hit things. And eventually some of them are going to bounce and just go straight through, and then they'll start bouncing around in here, and ultimately what do we predict is going to happen? Probably going to end up with about 2 particles on each side, right? It'll be the same. It'll come to like an equilibrium, right? When this gas expands, so when it moves over here, it's going to increase its volume, right? But as it's expanding, the pressure that it's expanding against is 0, and so the work is also 0. Do you remember work? Pressure volume work? So work is equal to the pressure times the change in volume. So a gas expanding against an external pressure is doing work. Here, there's no external pressure, so even though the volume's expanding, there's no work being done. There's no Q, there's no heat being exchanged. So when this gas expands to fill the entire system here, there is no change in energy. Everybody okay with that? but the entropy changes. And that's why it spreads out. So after you open that stopcock, we have several different states that are possible, all with the same energy. We're only going to look at 3 of them. So we could look at state A, where all of the particles are in the left side, state B, where all the particles are on the right side, and state C, where we have 2 particles on each side, all energetically equivalent. How many microstates are possible for each of these? How about this one? Like if we gave these particles names A, B, C, and D, is there another way we could arrange them? Maybe let's do C first. I'm going to call this one A, and this one's B, and that one's C, and that one's D. You can kind of see that. Could we have a microstate where instead of A being over here, A was over here and C was over there? Yeah. So that's a microstate of this one macrostate. How many different possibilities are there? A bunch. Yeah. That's one of those statistics things, 2 to the n or something. More than a couple, right? How about for state A? How many microstates are there? Just 1. All the particles are over here, and so the state is all the particles are over there. We can't say, well, we're just going to swap these individual particles. We're not going to go so in depth as to talk about the exact position within there. We're keeping it simple. And for state B, there's also only 1 microstate. Does that make sense? All 4 particles are on the right side. All 4 particles are on the left side. Here we have 2 particles on the left, 2 particles on the right, but then we have options for which 2 particles are on the left, which 2 particles are on the right. So that's different microstates. So which of these systems or states has more entropy? C. C is higher in entropy. And which of these 3 states do you think the system would go to? State C. Right? We kind of just know that from experience. It's not going to stay like this. It's not going to have everybody move to the other side. It's going to end up like this, where it's evenly distributed. But the driving force there is an increase in entropy. Any questions? So here they labeled them 1, 2, 3, 4. So for state A, the 1 macrostate, there's only 1 microstate. For B, there's only 1 microstate. State C, I guess it has 4 different microstates. So we could have 1 and 2 with 3 and 4. We could have 2 and 3 with 1 and 4. How is that 4 states? Does that look like 6? It is 6. It's, yeah. Mm-hmm. Yeah. 6 different microstates. And so they're shown there. This is sort of what I envision happening on Saturday at my son's wedding. You know, the photographer gets up and then you have to have like all the different combinations. It's like, well, here's the bride and groom with her parents, the bride and groom with his parents. Okay, let's have the bride and groom with all the parents. my husband's Japanese. You can just imagine. That stereotype is true. Oh, the cameras. Anyway, do you see that? So there are 6 different microstates. The probability of finding atoms in state C is actually 6 times greater than in state A or state B. And that's because of this entropy is equal to Boltzmann's constant times W. Natural log of W. Thank you. I was like, there's got to be something else in there. Natural log of W. If we increase the number of atoms in that system to 20, then we end up with 184,756 microstates for state C, where you have equal numbers of atoms on each side. But like if you had one more atom on one side than the other side, you'd have a whole other bunch. The number of microstates for A and B, where you have all the atoms on one side or all the atoms on the other side, remains 1. So the change in entropy from state A, where there's 1 microstate, to state C, where there's a gazillion, is positive. So the final entropy, the entropy of the state where we have atoms distributed between both flasks, and the initial was the entropy of the state where all the atoms were in one flask. And so by the gas spreading out, we have an increase in entropy. Does that make sense? So when the atoms are confined to one flask, their energy is also confined. When we allow the atoms to distribute between both flasks, their energy is also distributed over a greater volume. So energy is dispersed, and that also corresponds with an increase in entropy. So the second law of thermodynamics helps us to explain things that the first law of thermodynamics cannot explain. So ice water, here we have a beaker with ice water. The ice is cold and the water is less cold. And we understand that heat is going to move from the water into the ice. The ice will gradually melt. It never happens the other way, that the ice gets colder and the liquid gets warmer. It just doesn't happen. So the first law of thermodynamics does not prohibit that from happening. Doesn't say that's not possible. But according to the second law, energy needs to be dispersed and not concentrated. If the heat was going into the liquid, this was getting warmer and that was getting colder, that would be a concentration of energy, making it less spread out. That would be a negative entropy. Here, where the heat is spreading out from the water into the ice, it's dispersing. That's positive entropy. You familiar with the fun children's card game called 52 Card Pickup? Mm-hmm. No. You take a pack of playing cards and then you just kind of bend them and flick them and they fly all over the place. Okay, pick up the cards, right? That is dispersal of playing cards, right? And that's something that happens naturally. How do you get the cards back into a deck? You expend your personal energy to bring them back together, right? So here we have heat spreading out like those cards. Happens with Legos too.